following series is convergent or divergent. So here we got, there is no sign, means positive, negative, positive, negative, positive, negative, etc. So this is an alternating series. Okay. Now let's write this in terms of sum notation. So this one is same as sum n from 1 through infinity of, so to get plus minus, that is always negative. Okay, that's negative 1. Okay, negative 1 raised to n minus 1. My bad. Because when n equals 1, this is negative 1 raised to 0, which is positive 1. When n equals 2, that's the second term, negative 1 raised to 2 minus 1, 1, that's negative 1. So here is negative 1. So when we need to produce positive, negative, positive, negative, positive, negative, we need to write negative 1 raised to n minus 1. On the other hand, if we have to produce negative first, positive, negative, positive, that is negative 1 to the n. Okay, so that's that. So we took care of the sign. Next, 1 over 1 over, so this is 1 over natural log of n. Hold on, this is 2 though. When we plug in n equals 1, we get natural log of 1. But we are supposed to produce 2. So n plus 1. Let's try. N equals 1 gives us natural log of 1 plus 1, 2. That's here. And this one gives us positive sign, 1 over. And when n equals 2, that's the second term. Negative 1 raised to 1. That's negative 1 over natural log of 2 plus 1, 3. So this is good. Now the whole thing is an, and without this positive, negative, this is bn. Okay, the bn for the alternating series, 1 over ln of n plus 1. Okay, now we need to figure out if these bn's are decreasing and if they decrease to 0. If those two things happen, then by the alternating series test we can confirm this series converges. Okay, two things. The bn's should be decreasing. That means we need to check if bn and the next term bn plus 1 is smaller. Okay, question mark. If that's true, and second, not only bn's decrease, they have to decrease to 0. If that is 0. So if we are able to show these two things true, then this series converges. Okay, if one of them fails, we cannot conclude anything. Okay, we cannot apply the alternating series test. But look at 1 is always fixed. When n is really big, natural log of infinity is very big. Natural log of very big, kind of this in limit notation, that's infinity as well. And 1 over infinity is 0. So at least they go to 0. The second part is true. How about first part, if they are decreasing? So let me write formally here. So the next first bn is this 1 over n plus 1. We want to see if the next term n plus 1 means now n is n plus 1 means n plus 2. If this is true, okay, this is true if and only if we kind of cross multiply, this one goes here or this one goes here, ln, let me write this way, is, so this way means pointed part. I maybe let's write this way, maybe this one first, n plus 2, then bigger than equal to this way, or we could have written this less than equal to this. Is this true? You can check, take n equals some number, very big number, n equals 5, natural log of 5, is natural log of 5 bigger than or equal to natural log of, if I take n equals 5, this is natural log of 7, is that bigger than natural log of 6? Yeah, because that's true. You can check in your calculator or look at the graph of natural log. Natural log is a slowly increasing function forever. So after 1, this function is always increasing. So this is true. This is true for n bigger than or equal to 1. Okay, so this is true for n bigger than or equal to 1. So we know this bn's decrease is the limit 0. Yeah, we already checked that. Limit n going to infinity of bn is limit n going to infinity of 1 over n plus 1. When n is natural log of n plus 1, when n goes to infinity, this is natural log of infinity, which is really big, and 1 over really big is 0. Okay, so these two conditions are satisfied, then by the alternating series test, the given series converges, or the series is convergent, same thing.